for x given the information.
This call is now being recorded.
All right. Thank you for that, Sharabil. We actually been waiting for the record since the network was giving us some issues. All right. So to continue, in the previous example, when we were dealing with the univariate, we found the expectation of x to be 100 and the expectation of y to be 5. Let's not forget that expectation of x is the mean, and then the expectation of y is also the mean for the second variable, which is y, the second random variable, which is y. Now we calculated the conditional distribution for x given the information that y equals 0 by dividing each element of the top row of the preceding table by probability of y, that's the marginal probability at 0, which is equal to 0.50, which we have given in this table here. Can you see? For y equals 0, the marginal probability is 0.50, and for y equals 10, the marginal probability is also 0.50. Now, we did that calculation. So we found that the conditional distribution was used to find the conditional expectation. So the conditional expectation, or the mean, of x given y equals 0. Let us not forget this notation. We say that this of x given y is the conditional random variable, then equals 0. The 0 there is the value that this conditional probability can take. So we say for us to do that, we need to multiply the individual values times their probabilities, and sum it. We need to find the summation. Remember, expectation is summation, especially if we are dealing with the discrete case. So we need to sum the individual probabilities just like we did before with the values, the values that the random variable can take. So we have, for the first case, we have 90 times 0.10 plus 100 times 0.54 plus 110 times 0.36. So this gives us a mean, a conditional mean of 102.60. Now, we can repeat these steps to find the conditional distribution of x and the conditional expected value of x given that y equals 10. Now, in doing that, we do the same thing. Remember, look at the notation here. We have expectation of x given y, that's the conditional expectation, when the value that we can take is 0, as we can see from here, 0, y takes the value 0. Then here is the expectation where y takes the value 10 here, as we can see. So if we do that, we look at the values, the probabilities where y takes the value 10, and we multiply by the value. So we have probabilities multiplied by the value. So we have 90 times 0.30. That's from that joint distribution table. Then plus 100 times 0.66 plus 110 times 0.04. So for the joint conditional distribution, the conditional expectation for this condition where the value is equal to 10 is equal to 97.4, while for this other condition where the value equals 0 is equal to 106.60. Now, up to this point, all the materials that we'll be using in this example is a review work. So now the new insight in this example that we want to talk about. Remember, all these things I'm explaining, we have done it in the other class. So, but this particular class, the new insight that we're trying to derive comes from the observation that the two conditional expectations we have just calculated are values of a new random variable, which depends on y. So we might see this more clearly if we create a probability table. Now, from that other probability table, from the values we get and the probability table that we have, here we see y taking the value 0 and the marginal probability was 0.50, and here we have y taking the value 10 and the marginal probability is 0.50. Now we have the conditional expectation for y taking the value 0 to be equal to 102.6, and then also the conditional expectation for y taking the value 10 is 97.4. So this is another new table. This gives us another new insight based on what we're doing. All right, to forge ahead, the numerical quantity, which is the conditional expectation, depends on the chance event that either y equals 0 or y equals 10 occurs. Yeah, so if you have been with us from the previous classes and you have been following what we are doing in the previous classes, I'm sure that the explanation I'm giving now is not something that is strange, right? Hello, are you with me?
Yes.
Yes,
Yes.
yes. All right, that's great. So we can find the expected value of this new random variable in the usual way. So this new random variable that we have uh, here, we can find the expectation by doing the same thing. You see, by doing the same thing that we did to get this particular values, whatever we did here for the value of y equals 10, the conditional value for y equals 10, and then we also did for y equals 0. So here we're having another insight and we're doing the same thing. So we use the same formula to obtain it. So our marginal probability is 0.50 multiplied by the conditional expectation, which is 102.6, plus the second marginal probability, which is 0.50, times the new insight that we have, the conditional expectation for y equals 10, which is 97.4. So when we do that, they all give us the value 100. So the expected value is equal to 100. So now, the above equality holds for any two random variables x and y. All right. So double expectation theorem for expected value. Now, the idea of what we just did, this new SI that we have now, is talking about the double expectation. Remember, we've already talked about the conditional, single conditional expectation when we started the bivariate, when we start dealing with the bivariate distribution. So we took the uh, conditional expectation for each of them singularly. So now we're taking the double expectation, and with the example that we just did, gives us an idea of how to get a double expectation for these values, the two bivariate data values x, random variable x and y. So with that, we see that if we take the expectation of the expectation, I don't know whether that it looks somehow right, but I think that's what we're doing. If we take the expectation of the expected of the conditional expectation of the value of x given y, we're going to get the mean of x. Then if we take expectation of the value of y given x, or the conditional expectation of the value of y given x, we get the expectation of y. I believe that this theorem is understandable. So if we take the expectation of a conditional expectation, then we now get the value of that expectation. Then if we take the same thing with the second one. So if the condition is y, then the expectation of that conditional expectation is equal to expectation of x. But I don't know, does it sound confusing?
No, not really.
Okay,
Now,
all right.
using the example given above.
Yeah, exactly, correctly. All right. So in this case, we will not give any proof. Uh, But the only thing is that we'll just ask you to verify that the expectation of the conditional expectation of y given x is equal to expectation of y for the two asset example in exercise 11.26. Well, that's not an assignment, but you can verify. I believe you understand what I'm saying. It's not an assignment, but if you need additional understanding or knowledge, you can verify. Now, this particular material I've sent is on the drive. You can go and access it. That's probability for probability theory for what's the name, sef? Probability theory for risk assessment. Yes, that's the name. It's on the drive. Probability theory for risk assessment. You can look for the material to verify this particular uh, expectation, this double expectation.
Okay.
Now, yes. Now, example. So let's look at an example that looks more practical. The above the above example we looked at and the theorem is somehow abstract, but let's look at this example, which is more practical and will give us more insight on taking a double expectation, especially as it regards the conditional expectation. Now, example 11.29, the probability that a claim is filed on an insurance policy is 0.10. Only one claim may be filed. This 0.10 is the same thing as 10%. Only one claim may be filed. When a claim is filed, the expected claim amount is $1,000. Claim amounts may vary. A policy holder is picked at random. Find the expected amount of claim paid to that policy holder. So this is the question. So let's look at the solution. Now, solution. Note that the expected amount paid to the randomly selected policy holder is not 1,000. I'm sure we know. Let's look at the question again. The probability that a claim is filed on an insurance policy, that's the probability, is 0.10. Only one claim may be filed. That's the condition. When a claim is filed, the expected claim amount is 1,000, which means we have not selected, we didn't say that a policyholder will get an expected amount of $1,000. No, we say that when a claim is filed, the expected claim amount in general is $1,000. Now we want to find the expected amount. If we pick a particular policyholder, what will be the expected claim amount that policy that will be paid to that policyholder? What we're trying to do now is to find the expectation of the expectation. I don't know. Is that clear? Is the example clear?
Yeah.
Yeah. So because there's a general expectation that this is the claim amount for any policyholder, which is $1,000. Now, but this, well, we want to find the expected amount that a policyholder taken at random will get. So, in other words, we're taking the expectation of the expectation. Now, solution. Note that the expected amount paid to the randomly selected policyholder is not $1,000. Only 10% of the policyholders actually file claims. All right. Now, to solve this problem, we need to identify random variables x and y for the double expectation theorem. So to solve this, we'll go back to our double expectation theorem. Remember the formula. We say the expectation of the conditional expectation is equal to the expectation of that variable that we're looking for. Now, first, let y be the number of claims filed by a policyholder. So here we have y, number of claims. If 0 claims, remember from the question, they say only 10% usually file claims. So if a policyholder file a claim, then the probability is 0.10 or 10%, 0.10 or 10%. Then if no policyholder file a claim, the probability is what? 0.90. We know probability is equal to 1. So if the probability that a policyholder file a claim is 0.10, then the probability that no policyholder file a claim will be 0.90. All right. So in continuation, let x be the amount of claim paid. We are not given the joint distribution of x and y, but we are given in words the value of the expectation of y, which is equal to 1. Now it is the expected amount of $1,000 paid if a claim is filed. If no claim is filed, the amount is 0. So that is the value of expectation of x given y. Because if it does, the expectation of x given y is equal to 0 is equal to 0. I don't know, do you understand? And the expectation of x given y is equal to 1 is equal to 1,000. Is it understandable?
Yeah.
Yeah, thank you. Now the average claim amount paid to any policyholder is, so now we are doing the double expectation. Now we need to take the expectation of the conditional expectation. So first, when the claim is 0, we have 90%, which is 0.90, times the expectation, which is 0, the probability, which is 0, plus when the claim amount is $1,000, we multiply by the probability, which is 0.10, and that gives us 100. Yeah, so which is clear from what we got in the double expectation. All right, so let's look at conditional variances. Well, so far so good. Is there any question?
No, not from me, please.
Okay. All right. Are you the only one in the class?
Yes.
Oh, no, it's all right. Let's go ahead then. So, the conditional variance, since the expected value of x is the expected value of the conditional means e of x given y, the reader might expect the variance of x to be the expected value of conditional variances. However, the situation is a bit more complicated. We will illustrate it by continuing our analysis of the two assets distribution. Right. So in the previous examples, that's specifically 10.7, we can refer that in the material. We found that the variance of x equals 40 and the variance of y equals to 25. Now to find conditional variances for x, we will first find the expected value of x squared given y, which is equal to y, and use the identity. Now, all right, so let's go ahead. So variance of x given y is equal to y is equal to the expectation of x squared given y, which is equal to y, minus the expectation of x given y equals y all squared. You remember the formula? The formula for
Yeah.
variance of x, yeah, correct. The formula for variance of x is equal to expectation of x squared in bracket minus expectation of x all squared.
Yeah.
So extending it to that of the bivariate, we have the quantity here.
So yeah.
Now, when y is equal to 0, we have the following conditional distribution. So this gives us the joint table. So at 90, we have 0.10, at 100, we have 0.54, at 110, we have 0.36. Now, then the expected value of x squared given y is equal to 0 is 90 squared. So we are joining everything now. 90 squared times 0.10 plus 100 squared times 0.54 plus 110 squared times 0.36, just from the formula here. Then this second part will now take the expectation of the value, then we square it. That's all their differences. And 66. Then when we take the other part, which is 102 squared. So we have 10566 minus 102.6 squared, so which gives us 39.24 as the variance. So when y equals to 10, we have the following conditional distribution. Here in the table, just like the former. Then we repeat the same step for this table. Now when we repeat the same step, we have 27.24. So now, creating our joint, our double expectation, double table, we have what we have here, just like we did with the double expectation, conditional expectation. Here we are dealing with the double conditional variance. So when we do that, we have this same table as we did, and then we use it jointly. When we do it jointly, we have 39 from this particular table now. We are looking at it from this particular table. So when we do it jointly, we have 39.24 times 0. So now we're taking the expectation of the variance. So we have 39.24 times 0.50 plus 27.24 times 0.50, which is equal to 33.24. Yeah. Any question from here?
No.
All right. So let's forge ahead. Uh, is your time for the meeting ready?
Yeah,
Ready
I'll be
yet?
leaving in like the 5. I'm coming. Let me check. I'll be leaving in 5 minutes time.
Okay, it's all right.
Yeah.
So even when you leave, I'll just continue the class till I'm done. Then
Yeah.
it will be
When I'm through, I'll join again. But I have to.
it's all right.
Yeah.
Yeah, but in case you join and the class is already over, you just refer
Oh,
back.
not a problem then. I'm okay.
You
No
just
problems.
you
Yeah.
just refer to the recording.
Yeah.
But I'll send the material as soon as possible
Yeah.
this night.
Thank
Yeah,
you.
you're welcome. All right, so let's continue from where we stop. So in doing that, we should note that the taking the expectation of the conditional variance does not equal the value of the variance of x. Unlike that of the mean, that taking the expectation of the conditional mean give us the expectation of x, but here we observe that here it only gave us uh, 33.24.
Mm-hmm.
Yeah. So we should note that it is short by an amount. That's a discrepancy. So when you subtract 40 from 33.24, you get 6.76. Now, that's a difference and a discrepancy. However, we can account for the remaining 6.76. It is the variance of the values of the random variable expectation of x given y. So we repeat the table for this random variable below. Now repeating the table, we have these values as you can see here. For we have 0, the marginal probability is 0.50, and then the conditional expectation is 102.6. Then for y equals 10, the marginal probability is 0.50 and the conditional expectation is 97.4. Now the expected value of the conditional expectation of x given y was 100, remember?
Yeah.
Then the variance of the expectation of s given y is, so now we're trying to account for the discrepancy that we have here.
Mm-hmm.
Now, so when we take the variance of the expectation of s given y, this gives us 102.6, which is here, squared times the marginal probability plus 97.4 minus 100 squared times 0.50. So you see, it gives us what the value that is missing here. Remember, we say it can be accounted for. So this gives us 6.76. Now we have two expressions whose sum is the variance of x. Yes. First, we have for this, which is 40. Then second, we have for this, which is 6.76. All right, so what do we do next? So we have variance of x is equal to 40, which is equal to 33.24 plus 6.76. Yeah, so which gives us the sum of the expectation of the variance, the conditional variance, plus the variance of the expectation of the plus variance of the conditional expectation. So this identity always holds. So for the double conditional variance, we use this identity, which is you take the expectation of the variance of the conditional variance and sum it with the variance of the conditional expectation. All right. So the double expectation theorem for the variance. This is just what we just talked about here. See it here. This is just what we just talked about here. Yeah. So this is just a theorem to just emphasize it the more. So once if we're looking for the variance of y, then our condition, the only thing is that our condition in this bracket will change. It will be x giving y and x giving y. While if it is variance for y, then it will be y giving x plus y giving x here. But the same double expectation formula we used here, as you can see, is the same thing. It's just that this is for x and the condition change. The condition here is x giving y, whereas if it is for y, the condition is y giving x. All right. Likewise, we will not also prove this identity, but if you will wish to verify it, you can refer back to the material and try to verify for the two asset example in exercise 11.30. All right, so finally, let's look at this example and the solution, and then we'll be done for the class today. All right, so here is the example. We return to the insurance example in 11.29. If you want to read more of the beginning of the example, you can refer back to the material in the drive or our previous classes. In that example, we were given the information that the probability of a claim being filed by a policyholder is 0.10 and the expected amount of an individual claim given that a claim is filed is $1,000. Suppose we are given that,
Sorry, are you saying after this example you'll be ending the class?
yeah, I think there's no any other example. This is just the
Okay.
example.
All right.
Yeah.
No
So
problem.
once we finish this example, it's just questions and then thank you
Okay.
for listening.
All right. So I will be leaving now. So I'm going to come out and
Okay.
is that okay?
It's all right. So I will just continue with the example.
Continue. Okay.
Yeah. So when I'm done, it will be saved and then
So you say you're going to download the something as soon as possible.
yeah, I'll send this material as soon as possible to you.
Okay.
Like,
Thank you very much.
for the
Thanks.
video, it takes 24 hours.
Sorry? Yeah,
For the
you
video,
mentioned.
yeah,
So
yeah,
that means it might be available tomorrow.
yes, exactly.
Okay. Thank you very
It's all
much.
right. Thank you for joining the class. Have a great day.
And you too.
All right. So I continue. So we return to the insurance example in 11.29. In that example, we were given the information that the probability of a claim being filed by a policyholder is 0.10 and the expected amount of an individual claim given that a claim is filed is $1,000. Now suppose we are given that the variance of claim amount given that a claim is filed is $100. Find the variance of claim amount for a randomly selected policy holder. I believe that this question is quite clear because this is like an extension of the previous question that we looked at in example 11.31. Just that now we have another condition where it says that suppose we are given that the variance of claim amount given that a claim is filed is $100. So that's the new variation and the question is saying we should find the variance of claim amount for a randomly selected policyholder. All right, so let's move to the solution. Now, we have already identified the random variables involved. Y is the number of claims filed by a randomly selected policyholder, and X is the amount. Y is the number of claims, while X is the amount of claim. Number, amount paid to that policyholder. Now we have already found that the expectation of X is 100. Remember, to find the variance of X, we need to find the two components. And the two components are A, we need to find the expectation of the variance of X given Y. And then B, we need to find the variance of the expectation. Remember the formula for our double expectation theorem for the variance? Yeah, so that's what we're looking for. So here we find the first component, then we'll also find the second component. And when we have done that, we sum both components, which will give us the double expectation. Yeah, so in doing that, A, which is the first component, which is expectation of the variance of the conditional variance. So given that if claim is filed, the variance of claim amount is 100. Thus, the variance of X given Y is equal to 1 is equal to 100. Remember from our table? Now, when we say if a claim is filed, now if no claim is filed, that's 0. The claim amount is the constant 0. So the variance of X given Y equals 0 is 0. Remember when we did that? So then, to now get the expectation of the variance, this gives us, we will now multiply the probabilities by the value that the random variable can take. Remember? So this gives us 0.90 times 0 if no claim is filed plus probability 0.10 that a claim is filed times 100 when a claim is filed, which is the expected value of when a claim is filed. So this gives us 10. So now we have the first component. So we need to generate the second component and then we'll now find the double expectation. Now, the mean of the random variable expectation of S given Y is 100. Remember? So thus, we'll now find the variance of the expectation. So which gives us the expectation of X given 0 minus 100 squared times 0.90 plus expectation of X given 1 minus 100 all squared times 0.10. So here we already have the value of the expectation of x given 0, which is 0, minus 100 squared. So 0 minus 100 is minus 100. When you square it, you get 1,000. 10,000. 10,000 times 0.90 plus 1,000. That's expression of x given 1 is 1,000. Remember, we say when a claim is filed, the expected value is $1,000. So that's why the value there is 1,000. The value here is 1,000. So we subtract it from 100, then we now square everything. Then times 0.10. Now in doing that, we get a total amount to be 90,000. All right. So let's see how we can join the two values together to get our double expectation. Now we can now find the variance of x. The variance of x is equal to the expectation of the variance of the conditional uh, conditional variance plus the variance of the conditional expectation. So this gives us 10 plus 90,000, which is 90,010. All right, in conclusion, the student who has studied statistics may have seen the variance identity before. In the above example, the expected value of the conditional variance is the mean of the variances within each of the two categories y equals 0. No claim filed, that's when no claim is filed, and then y equals to 1 when a claim is filed. It is often referred to as the variance within groups. Yeah. So in statistics, when we're looking at variance, there's what we call variance within, variance, and so on and so forth. Between, within, between, they have different way of calculating them. Now, the term V of the variance of the expectation of S given Y is the variance of the means of the two groups, and it's referred to as the variance between groups. So yeah, so that's what basically what it is. There's the variance within groups and there's the variance between groups. All right. So so far so good. Is there any question from anyone? Yeah, I'm sure there's no question. So far so good. In recap, we have talked about the conditional expectation. We also talked about we use an example to verify the conditional expectation. Then we looked at the double conditional expectation. Yeah. So after we looked at the double conditional expectation, we also look at the conditional variances. We added some other extension, and it helped us to get a double expectation theorem for the variance. So just like we got the double expectation theorem for the mean, so we did that. We say that the proof is just to verify. We don't need to do the proof here, but anyone who wishes to verify can confront the textbook at the drive. Yeah, we also look at this example and we see how we can be able to calculate the double expectation for the variance. We discover that we find the expectation for one of the components, then we also find for the other component, that's for the expectation of the variance. Then we also find the variance of the expectation, and then we sum the two of them together to get our value. So we did that, and we got the uh, the double expectation for the example that we have to be 90.01. All right. So without any more questions, I would like to say thank you for listening. Thank you for being part of our class. I do hope that in our next class, if there are other reviews and questions, we will get them. Now, additionally, we will post this particular material in the drive. Also, the video too will be posted on the drive. So let's do well to consult it. And when we come in our next class, if there's any question, we'll look at it and then we'll talk about it together. In our next class, we'll be looking at the bivariate normal distribution. We'll look at its PDF we'll look at some other things that we can get from it, some properties. We'll also look at its application in actuarial science in insurance. So we'll see all these things in our next class. We'll see the importance of the bivariate normal distribution, and then we also have what we call the multivariate normal distribution, but we are only going to look at the bivariate normal distribution. So thank you for being part of the class. I do hope that it has been insightful, and we will meet in our next classes. Have a beautiful day ahead, everyone.